Swayam Prabha. Digital India. Educated India.
Good morning. Welcome you all to this lecture in the series on analytical, spectral and microscopy applications of inorganic compounds and nanomaterials. In the past couple of classes we have been looking at one of the spectroscopy technique which is very commonly used both for the organic and as well as the inorganic compounds. That is the vibrational spectroscopy, which is popularly known as infrared spectroscopy and a lot of Raman spectroscopy as well. And we have looked at the very basic concepts of these and the principles associated with this, the transitions. One case you have absorption, in another case you have a scattering phenomena, both different. And also we have been able to look at and understand that the spectra that you obtain from the infrared and that of the Raman are complementary to each other, together will become the total vibrational spectroscopy. In the process we have been going through, just like many, for example in NMR we have seen the different chemical shift ranges for various proton and proton NMR. Similarly we can always look at even the vibrational frequencies. We talked about the vibrational frequencies mainly in the fingerprint region. Particularly the fingerprint region is the term fingerprint has come because you can use that as a thumbprint, so you can match and then identify and then assign, and that is what basically the thing is that. Okay, so when you are looking at the frequencies, you need to look at the reduced mass, which I explained to you in the earlier classes, and whether the bond order is a single or double or triple or of course any in between. So there is force constant which is referred as. This is also an important aspect. If not the direct bond, if it is a group, of course it is a group, the force constants need to be utilized. Primarily these two have to be kept in mind in order to look at that. We have already looked in the previous class, I'm just taking a browse through, is that the region, as you can see, draw your attention to this particular slide, which of course I have explained earlier, but I will just bring once again to you the OH, NH, CH, stretching region, both the symmetric stretching as well as asymmetric stretching. Generally asymmetric stretching is a higher in energy because asymmetric stretching requires a more tougher than that, so greater energy. Then you will have at least 100 wave numbers or more higher than that of the symmetric thing. So both will come very close to that, symmetric as well as asymmetric for OH, NH and CH region, which is somewhere between 2800 to about 3600 range or 3650 also. So all these three can be resolved out depending upon the groups present, etc. Then some region between 2000, 2500, 600 is somewhat for the triple bonded, like C triple bond O, C triple bond N, these kind of groups. Particularly the carbonyl chemistry is focused between 1900 to 2000 or even lower than that, 1800 or 1600, depending upon whether it is the terminally bonded or bridged or multiply bridged, which I explained to you in the previous class. So you can take somewhere from 1617 up to about 22 to 100, etc., and then Cl nitriles and then carbenes, all of these kind of things. Then comes a little lower to that, maybe from 1700 below, you will get this double bonded ones like CO, CC, CN, all these, their variations as you go from one to the other. Then comes is lower to 1100, 1200 and below. In that range you will find single bond ones, C single bond O, C single bond N, C single bond C, and further below you will get the C single bond S, etc., and further below you will get C single bond the halide CX, and then below that 600, in that range you will get the metal to nitrogen, metal to oxygen, these kind of vibrations, and metal halides will come below 350 and below. So these are the kinds of ranges that you have and which are used. And these are for the functional groups kind of thing. We can also look at when you have into the inorganic systems. So you can see that the inorganic systems, I already mentioned based on the previous slide itself, the metal to nitrogen kind of things, and the metal halides, and so those kind of vibrations come much below 500, 600, and goes much even up to 150 wave numbers, which is generally referred below 500 as the 4IR region. So these some of the spectra you see at the mid-IR, some of the cases you will also see the 4IR. Of course, bit of instrumentation is also differs to measure that. You will not be able to measure on the mid-IR instrument. Other groups like the nitrile, I've already talked to you. NCS, of course, is a part of what I talked, though not directly. CO, I talked to you. And the ammonium groups can give the stretching, bending, and rocking, all kinds of things. NH2 group can also give with reasonably characteristic. NO2 groups can give. And if it is bonded to metal to nitrogen versus metal to oxygen, and then carbonates and nitrates and sulfates, and of course the water. So all of these have got their metal to that ligating atom corresponding vibrations, as well as that group vibrations. And the group vibrations will be slightly modified because the group is anchored now onto the metal ion. So therefore certain symmetry related things will change, and even your vibrational frequencies will change. That is a boon in disguise, because you can say when there is a change in the main frequency of the carbonate, then you can say the carbonate is attached to the metal, or nitro group is attached to the metal, amino group attached to the metal. So that shifts are indicative of the binding to the metal ion. So these are the things which I have already talked to you and taken you through a quick tour through some of these inorganic compounds, etc. I have also explained to you very elaborately in the previous class about the carbonyl, so carbon monoxide to be very precise, though these are called as carbonyl complexes, is a carbon monoxide complexes binding in various ways. You can see all of them. The frequencies will change, and whether the metal complex is a neutral or anionic or cationic. I have not shown the anionic here, and of course those will go frequencies lower side, and the cationic will go to a higher side because you are taking out an electron to the metal. So therefore your carbon monoxide bonding order will be unperturbed or even strengthened. So therefore you get a higher frequency than even the free. Similarly, if you go to the negatively charged complex, then you have an extra electron being put into the complex, and this electron can perturb the CO bond order. So therefore your bond stretching frequency will slightly reduce. So this is where we have also looked at another example of a coordination complex of the vanillin salicyl hydrazone in the free form, and when it is bound to iron, when it is bound to nickel, and you can see the corresponding differences in the vibrations, and based on that you can talk about the complex formation, etc. So all of those are there. Now let us look at some specific application based examples of using the IR spectral data, etc. For example, now we will look at for the nano systems, and one of that given in this particular slide, I draw your attention to this, is the silver nanoparticles, which are synthesized from aqueous medium, where the aqueous medium possesses the leaves, extract of the leaves of Utica dioica. Obviously, leaf extract has got a large number of components, including proteins, many other phenolic related compounds, many nitro based compounds, and all of these kinds of things are possible. Maybe some little bit of even halo based compounds also. So it will not be just one single compound, but a large majority will be a protein. So if you try to look at the spectrum of the silver nanoparticles, which were synthesized by taking through this particular solution medium, and of course you take a silver nitrate in this medium and then use some reducing agent, or it can be auto reduction also by these lot of molecules are present in this extract, and they themselves can act as reducing agents as well. They can cap. So therefore, using that also you can make these silver nanoparticles. And now its IR is measured, and that's what you are seeing here. Clearly you have in the region of the OH-NH kind of a region, and clearly in the region of CH, and then you have in the region of the some kind of a double bond, carbon-carbon double bond systems, etc. in this. Then you have the carbonyls and a few amide based bands, and you know that the protein has the amide group. The amide group has got the amide bands, amide 1, amide 2, amide 3 at least, which comes within this region. As well, you can have the in the range bit below that you can have the NH and CN of the amines, and then you can also have NO stretching or vibrations, and then CN vibrations, etc. All of these are possible. And way below you can have the carbon with a very heavy atom. Very heavy atoms could be the halides, for example. Here it could be the bromide, etc. So all that what you are seeing a signature of these all organic matrix, including good feel coming from the protein presence, and also feel coming from some different kinds of extracted molecules. We have some idea about what kind of a molecules are present in such a extract. They can be the phenolic based compounds, nitro based compounds, halo based compounds, so all of these. So they are all anchored onto the silver nanoparticle. So you're able to get an information that these are all. Of course, if you have a specific band for amide or for the protein, and then specific band for other compounds, you can take the ratio area. From the area you can discuss the ratio also in that, provided you get the bands separate, or you are able to deconvolute the bands, either of the case. So you can see starting from all these entire spectrum. So therefore, what one can conclude is from these nanoparticle infrared spectrum that the protein is still present there. Protein secondary structures are still intact, because that is where your amide bonds, etc., bands, etc. are coming. And there are of course few other components are also there in this, and of course you cannot exactly characterize those things, but you can say other than protein, yes, they are also there, and they all these are interacting with the silver system, but there is not much change in their secondary structural features of the protein even upon interacting with that, which means these proteins can still show their basic characteristics when you use these nanoparticles coated with such an extract medium for various purposes. So since this is only restricted to the infrared, we are not going into the actual application, what it is used for, but we are saying before it use it, you need to characterize, and that's what we are focusing on that. I hope that part is clear to you. Okay, so what all we are saying, we are looking at the infrared bands and then trying to conclude that what are the components that are present, and primarily the protein and other extracts like phenolic compounds, nitro compounds, halo compounds, etc. Beyond that is not the scope of this infrared spectroscopy part of it. Now, having looked at the nanoparticle, let us look at some composite. Most often people use a lot of graphene oxide, reduced, so all these kinds of things. And here this is with the zinc oxide being okay. So you can see that there are 4 spectra are there. This is the pure graphene oxide, pure zinc oxide, this green one, and the pure graphene oxide, the bottom one, which is black, and the red is graphene oxide with some amount of zinc oxide, so 60-40, and the blue one is the graphene oxide, zinc oxide 40-60. That means more amount of zinc oxide is being. So what are we trying to look at? We are trying to look at that when you put this zinc oxide under the graphene oxide, we are trying to look at whether these are interacting to each other, whether the zinc oxide formed its own structural features on the surface of the graphene oxide, and that's what we look for. So for that, what you see, you look at the graphene oxide various FTIR characteristic bands. In this region, there's another region here, there's another region, there's another, and all these. So you can just sit and look at all those 3100 to 600, and then 1600 in this OH, and we can say that a lot of water being absorbed on that. Also we can say there are a lot of OH groups, because you are basically functionalizing the graphene oxide so to different extents, through the oxidation process. So the oxidation process will result in hydroxyl, carbonyl, carboxylate, many related oxo kind of a moieties. So they are all characteristic. Of course, percentage of these can also be estimated even using the infrared, though that is not part in this particular example in that. So you can say that the graphene oxide has got the adsorbed water, and then therefore you have a good hydrophilicity that you have generated on the surface of the graphene oxide, and that would be required for some purposes which we are not discussing in that. In the mid IR, this is this 2750 2800 region, and these are the CH2 groups, and then comes is the 1600 range is your carbonyl, coming from carbonyl, and can be coming from other kinds of carboxylate groups because graphene oxide is functionalized. All of these are present. Okay, and then alcoholic OH groups are also present because when you oxidize partially these things. And then you have peaks around 750, then 1300, 1100, etc. all of these. So showing a lot of functionalization of the graphene oxide, and these functionalizations are holding, and if you look at this direction you will see the zinc oxide signatures. So zinc interacting with all these zinc oxide, zinc oxygen, etc. Of course, you will club this with the far infrared spectrum also to make the total, the structural feature evaluation in that. So these oxygen functional groups are created by oxidation route involved in the Hummer's method. But even after oxidation, the main structure of the graphite will be retained, and this can be checked from the graphene bands. The graphene bands are there. I will explain you in another example. So the graphene bands can also be cross-checked. You have the bands coming from the organic moiety, functionalization that has taken place on graphene, and the original graphene moiety where the characteristic bands are that. Of course, much more characteristic will come in Raman spectroscopy for the graphene structural features to be evaluated. So all this, what it tells, these different infrared spectra measured under different conditions like pure graphene oxide, pure zinc oxide, graphene oxide in different combinations will clearly tell that the graphene oxide is intact, and a lot of functional groups are involved, and these functional groups are bonded to the zinc oxide, and zinc oxide original bands will also be there, and therefore this material can be used as this composite material can be used for whatever the application that has been planned. So good characterization aspects of it. So we looked at in the previous case silver nanoparticles, in this case graphene oxide, zinc oxide, the nanocomposite. Let's look at some other example which is directly used for an application. Again, kindly draw your attention onto the slide where I am always showing the different regions of the spectrum in this. This is a nanocomposite film which is made from the agar. And to make this film agar sustainable for the durability of the green grape, use the zinc oxide nano. So what you do is zinc oxide nanoparticle being put into the nanocomposite. In the previous case, graphene oxide and zinc oxide. So now here it is the biocomposite film into which of the agar and into which you put the zinc oxide nanoparticle. And this whole thing, film, can be wrapped around these grapes, and the grape's shelf life will be longer. The grape will not get dried, will not get shrunken, etc. So therefore all of those can be prevented. So this is basically used for an active packaging for shelf life. So that is an application. Application part we are not showing here, but the characterization part only showing here, though the title shows up to that. So we have three infrared spectra. The control, only the agar film, which is red. So this is your biomatrix, agar matrix, which is in the form of a film. You can see all organic functional groups, OHS, CHS, CO kind of things, single bond ONs, etc., and then other ones. So all of these, you can see all of them are explained over here. Some CS3 groups, deformation, C single bond O, COC, all of these you can see that. Now let's say you put some amount of zinc oxide, which is about 2% in case of B, and is about 4% in case of C. So you can see that the original features of the agar film are retained, obviously. And of course, if you go beyond this, that means below this frequency, you will still see the zinc oxygen and zinc other vibrations as well. so one can see that, though it is not shown in this. So by comparing the infrared spectrum of the film with that of the composite attached with the zinc oxide, you can see that this is basically the zinc oxide forming a composite with this film. Now, how do you prove this packaging, which is not a part of this? Then what you do is you try to put wrap to that particular grapes, and over a period of time at every regular intervals, like once a day, once in a couple of days, etc., you check the film again and see how intact is that. So that means how long you can use this film, and you also physically inspect the grapes whether they are intact or not. So by comparing those physical inspection of these grapes with that of the infrared spectrum of the film, you can talk about the durability, how long you can use that kind of thing. So to look at the durability, obviously you have to take the IR after wrapping and taking out for some days, for more days, etc. So that is the kind of thing where you can extend the applications. Okay, so I hope that is also clear. And let us look at some understanding on the coordination complexes. How do we go about interpreting the frequencies in a comparative manner? So for example, here we have set of complexes MNH3 twice X2. So this MNH3 twice X2 is a square planar. Of course it can be tetrahedral, but these are square planar ones which we are talking about. Twice X2, this is the, so square planar complexes you know very well from the coordination chemistry. One of the features is the cis, other feature is trans. So this is one of the factors. Then I can change the M here, the platinum, palladium, etc. I can change the X, so X could be fluoride or chloride or bromide or iodide or even nitro or sulfato. So any kind of things, very many of these things are possible. So here we are restricting to the set of halides, set of metal, and this one. So what is that importance? Now if you can recall, I talked to you that the new frequencies of the vibrations are proportional to square root of k by mu. Okay, mu is the reduced mass, which the reduced mass is that if you have a mass with m1 plus a mass with m2, this is the inverse. 1 by the inverse of reduced mass is equal to the inverse of mass of the one of them plus the inverse of the mass of the other, and these two, this is where. So that means it is dependent on the mass of this, and you know the platinum versus palladium, the mass difference is there, quite substantial, you can see. Similar is the case with the X. So this will lead to M is bonded to N, so we can look at the vibrations of this, and M is bonded to X, and then these vibrations. So all that you will find is the vibrations of Mx and Mn. So these are the things, and they get affected by changing the M, by changing the X, okay, and both the cases by changing the cis versus the trans, because the symmetry has a lot of role, though we have not gone in this particular course on the infrared. The greater the symmetry, less number of bands. So greater symmetry, less number of bands. Lower symmetry, higher number of bands. So these are, you can take it as granted, which has been well proven and then seen beyond all. So if you use these concepts which I mentioned, you can understand this table. Otherwise you think that do I need to mug the table? No, you don't need. You need to analyze the table in comparison. Okay, so you can see for example here you have the palladium with the, in the case of chloride, with the Mn around 490 range is the stretching frequency at that. And if I go to platinum for the same, you can see you will get around 570 in that range. So that is what, around 80 centimeter inverse difference. The reason is very clear, is the mass difference that you have between the palladium and the platinum. So you understood one. Okay, so come on this side. I should have first talked about this, but anyhow, nevertheless, let us look at this first. Now, and this spectrum is for the trans, and the one below is for the cis, or the same compound. This is palladium diamine dichloro, both trans and the cis. What is the difference you are seeing? You are seeing the frequencies almost at the same position, but you see one additional difference. So this one band here in trans look like a doublet. The one single band here looks doublet. One single band here looks double. So why? Because cis is less symmetric than that of the trans in very rough terms without going into the pine group and other things. Okay. So the greater, so that is where each of the band is further split into two parts. So the palladium nitrogen band, palladium halide carbon, here you can see this also, even other bands as well. So other bands are coming from the ammonia group, etc. So even there you have, so you see the ammonium bands splitting as well as the metal. So that is the frequencies of vibrational frequencies of NH3, whether it could be nu, it could be delta, it could be rocking, etc., any of these things, as well the nu of Mn and as well nu of Mx. So all of these you have seen the difference. Okay, so I hope you notice that. So number one, so we have proven this part of it, cis versus trans, the number of bands and that. So just prior to this I explained to you the nu Mn, which is for the palladium N versus the platinum N for the same type of complex. Both let's take as a trans, as I told you, in the range of 490 and in the range of 570, which is the difference is around 80 wave numbers. So if you put the reduced mass into this formula and then find out, you will see, and you can make a good match also. That is how people pair. And now let us look at another point of metal halide. So the metal halide, okay, so let's take platinum case. So the metal halide, this is the chloro MCl here, MBr and Mi, three cases. So MCl is around all I am taking for one case, that is a platinum case, so 365. We will take the antisymmetric, all the cases. You can also take the symmetric one. Symmetric one is a lower one, asymmetric one is a higher one. And bromide, yes, we have. So 260, see, 100 wave number difference. And this iodide, do you have? Yes, we have 153. So I think this is for the symmetric instead of antisymmetric. It doesn't matter, roughly around 150 to 160 range. So you can see about 100 wave numbers, you can see about 100 wave numbers. So this is again explains you the difference of chlorine versus the bromide versus the iodide. Again, mass effect. Of course, their electronegativity will change force constant as well. Force constant is not the same. The force constant will also change, but that will be changing somewhat, not so dramatically, but the mass is changing very dramatically. So both of these. So we have looked at these ones, we have looked at this example and all of these that we have. So this entire table is not just the numbers, but the numbers for comparison purpose. So similarly, even some bending vibrations are also there. One can compare even that. So the stretching, the bendings will come much lower than this. Here you have only up to 300, 350, but you can go much below. As I said, the far infrared kind of a spectroscopy. Okay, let us look at one other example before we close this particular lecture. Is that in a series of the metal ethylene tris ethylene diamine, that is 6 coordinated, and a sulfate, that means 2 plus. So it's a 2 minus is outside, 2 plus is inside, so therefore. And now if you look at, so these are nothing but the metal so this is tris, so you have sulfate 2 minus. So you're looking at the Mn band vibrations, nu Mn, vibration. So these are the things. If you look at a series of compounds where the M is, earlier I talked to you about the down the group now within the same period, so that manganese, iron, cobalt, etc., nickel, copper, and this, if you look at this vibrational frequency, I draw your attention to these particular numbers, which is the symmetric stretch and the top mu4, and the asymmetric stretch in the nu4, and symmetric stretch in the nu5, because nu5 is smaller value than that nu4, and that we know that asymmetric stretch comes at the higher. See the trend, this less than this, less than this, less than this, less than this, and greater than this. This is what exactly the Irving-Williams series shows for the stability or the metal divalent transition metal complexes with the ligand given same ligand across all, and this is across all ethylene diamine. So therefore we can make a comparison. If it is different kind of ligands, you should not make, that's wrong comparison. So all of them are bound to 3 ethylene diamines, all of them are in octahedral, all of them are 6 coordinated, therefore you can compare. So this order is exactly analogous, similar to that of the Irving-Williams series of the stabilities, thermodynamic of course, of the divalent transition metal ions towards a given ligand. Okay. So another thing is Raman spectra of some chloroamine cobalt 3 complexes have been assigned. The series chromium NH35X2 minus. So if you look at the CRN, so they are in the range of 400 to 475, and the CRX are dramatically changing. You know why? 540 could be for fluoride, it could be 300 chloride, 260 bromide, 180 the iodide. So you can see how well. So shown another, even from the Raman one can see all of these. So immaterial, it's a vibrational is important, which is that IR or Raman is not the important one. Okay, so I think I have many more examples to deal. I think I'll be able to take one more class on this to complete the vibrational spectroscopy of both Raman and infrared. Thank you very much.